participants have joined and they are joining. We can start, please. Brother, you are not audible. Please continue.
Let us start the session. Participating now. So I
Jadavda, you are not audible. Jadav sir, you are not audible. Please check.
hello. Right now I'm audible right now.
Yes, somehow it is lagging. Please
Audible.
continue.
Hello.
Yes, please continue. It is audible now.
Hello.
Yes, Jadav sir, please continue.
Okay. Thank you. So I'd like to briefly introduce. Okay, I'd like to introduce shortly Professor Dr. Urvashi Sinha before hand over the session to her. So Professor Dr. Urvashi Matter Physics Group at Raman Research Institute, Bangalore, India. She is also an affiliate member at the Institute for Quantum Computing, Waterloo, Canada, as well as the Center for Quantum Information and Quantum Computing at the University of Toronto. She has recently been awarded a Homi Bhabha Fellowship. Over the last 10 years or so, she has been doing quantum optics based experiments primarily targeted towards testing fundamentals of quantum mechanics as well as quantum information and computing. He is the invited country representative of the Geneva Science and Diplomacy Anticipator Open Quantum Initiative Core Task Force June 2021 onwards. She is the invited Indian representative for the World Quantum Day Network, a global network of quantum physicists who are engaged in promoting and showcasing quantum science and technologies through diverse nature. She was the member of the Draft Project Report Committee for the National Mission on Quantum Technologies and Applications 2020. She received ASCOM Women in Cyber Making a Difference award in the category Cyber Leading from the Form 2021. She is the winner expert member in the two-member winning team of the World Skill International Competition in Quantum Technology at the BRICS Future Skill Challenge, organized by Russian Quantum Center in Moscow, Russia, with competitors from several countries worldwide. She has more than 150 international journal and conference publications. Her research interests includes quantum mechanics, quantum computing, quantum optics, quantum communications, nanotechnology, device fabrication, superconductivity, and so on. So I welcome Professor Dr. Urvashi Sinha on behalf of the organizing committee, and we are thankful for giving us your valuable time. So, ma'am, please.
Thank you very much for the very kind introduction. Am I audible?
Yes, ma'am.
Great. Yeah. So thanks very much. And of course, thank you to the organizers for giving me the opportunity to talk to you today. I'm very happy to be doing that. So I just want to ensure that you can see my slide. and things are working?
Yes, ma'am. It is
Yeah,
visible.
great. Yeah. So thanks a lot. And I hope, over the next hour, I get to communicate some of the excitement that we have at RRI, Bangalore, towards our research in quantum communications. So, of course, the program is on quantum computing and its applications, from what I understand. Quantum communications is not quite an application of quantum computing, but it is more an application of quantum mechanics. And it is, of course, one of the most interesting and one of the most technologically advanced quantum technologies. And we will see how it is connected to quantum computing, in the sense that it is very necessary for us to develop research in quantum communications to ensure that some of the threat that is posed by quantum computing in some applications is mitigated. So that is something I will explain as I move along. The underlying feature which we work on at our lab at RRI is basically based on this particular quote, I would say, that today's science is tomorrow's technology. And so we are invested in lots of experimental and theoretical investigations of scientific aspects of quantum domain and their applications in the technological domain as well. So we basically investigate both sides of the coin, let's say, at our lab at RRI. And of course, as was mentioned, there is a national mission that has been planned by the Indian government on quantum technology and applications. And of course, I was a member of the drafting committee for this DPR, and we hope that this is going to see fruition soon. And I think quantum is slowly and surely becoming a very important area of research in our country. And as such, this emphasis on both fundamental science and technology continues to retain a lot of importance. Okay, so as participants, okay, not entirely sure. Okay, so as was mentioned, I belong to the Light and Matter Physics group at RRI, and while I head the Quantum Information Computing and Communications Lab, my colleagues are also working on different areas of quantum technologies, some of them working on quantum optics, quantum interactions, quantum mixtures, as well as ultra-fast optics and lasers. Okay. Before I go on to quantum communications, which is the main focus of the talk, I'll give you a very, very brief overview of the different activities that our lab is involved in, which are not related to quantum communication. So, you get a holistic perspective of the kind of work that we are doing. And of course, on a better day, and let me see if I can get my pointer to work. Yeah. So I hope that's working. So this is, of course, an overview of, different experiments as they are happening in the lab. And we are used to having lots of visitors in our lab. But then, of course, 2020 onwards, that has been difficult. But what has been enabled is for me to sit here in Bangalore and talk to people in West Bengal. And so, there are again two sides to the coin. And I hope we go to a happy mean at some point in the near future. Okay, so the basic underlying technology on which all our science is based is what is called a single photon. And of course, you're aware of what that is. That is a single particle of light. And what one has to understand is that, when one is dealing with quantum oriented research, we have to deal with the single particle, because, that is where various interesting things emerge, whether it's a single particle or maybe pairs of particles or more particles which are entangled with each other, and so on and so forth. So this is a popular review that I was invited to write, and you can have a look at this if you're interested in different methodologies towards manufacturing these photon sources, because as opposed to what one might think, we are of course I'm sitting in an area which has a lot of light, and so you would think that working with light will be light and straightforward, but that's not true. You cannot just dim down the light and get it to a quantum level. There are dedicated technologies which one has to employ towards making these photons. And so there are different ways of doing this. And this article will give you an overview of some of these ideas. What we are working on specifically in our lab right now is what is called spontaneous parametric down conversion, which is a nonlinear optics based process. Okay. And so here, these photons that are produced, they come out as pairs And so pairs of photons, they actually traverse cones in space, and that comes out as a result of energy momentum conservation relations and equations and so on, which I won't get into. But then the underlying thing is that, if one of the photons, let's say, belongs to this cone on the right, its partner photon or twin photon will belong to the cone on the left, so that you have momentum and energy conserved. But then having said that, if you actually look at this intersection point here, this is a point which you do not a priori know whether the photon belongs to the right cone or the left cone, because it could belong to either. So if one of them belongs to the right cone, its partner will belong to the left. But before you know the first, you do not know what is happening with the second. And this is what defines an entangled state. Just wanted to confirm once that I'm still audible, because there was a bit of an internet connection in the beginning issue. Dr. Das, am I audible? Or anyone else can just confirm?
Yes, ma'am, it is audible,
yeah, great.
ma'am.
Yeah, but I have, during this last 1 year, there was one talk that I have given in which 45 minutes of the talk, the people had lost connection. So I have become a little bit wary, so every 15-20 minutes, I just confirm once that everything is okay. So having said that, this is where we are, that, this is an entangled state, okay? And this is a picture of our actual source from the lab and so on. So as I said, that I will spend 3-4 minutes in giving you an overview of the different areas which we are working on. One of the very important areas that we are investing a lot of time and energy is in fundamental tests of quantum mechanics. Now, of course, the theorists in the audience will know that, a lot of the universe is something which we do not really understand what it's made of. Right? 80%, 85% of the universe is unknown to us. So there is a lot of things which is left to be discovered. And so it becomes very important that we have dedicated tests for the various laws of physics and for the various principles, and for, in our case, quantum mechanics, so that we understand them as precisely as possible, so that the applications which we are then applying them to also gain from this precision understanding. And so precision tests of fundamental aspects of quantum mechanics and quantum optics is something which we continue to be very fascinated by. And so this is a body of work we have done in which we have, challenged the common usage of the superposition principle in interference experiments and shown, both through theory and experiment, that we actually need a correction term. It is incompletely applied in common applications. It needs a correction term, and this is a measurement, first such measurement of the correction term that we did in our lab. Okay, this is a fundamental quantum optics exploration where, again, there is an effect which is called the Hongo-Mandel effect. Maybe some of you are aware of this. This is one of those quintessential quantum optics phenomena and is used as a diagnostic test for whether you have a single photon or not. And so what we went on to do is challenge this concept and say that, okay, I can actually get high visibility, in fact, 100% visibility Hongo-Mandel dip by using classical pulses with phase modulation. And we went on to do the experiment and show that as well, and kind of proposed that instead of the Hongo-Mandel dip, one has to use what is called the complementarity effect to test for the signature of quantum. Okay. One of our recent works is something which has ramifications in quantum communications, among other applications. This is a very precise quantum state estimation technique. Okay, so now when you've been hearing many talks on quantum aspects of the matter, so you've realized that one of the fundamental objects, or one of the fundamental entities in quantum is, of course, the state itself. So what is the state of the system that I'm dealing with? So now, if I want to know, what is the quantum state, I just cannot measure and know it and leave it undisturbed. As you know, quantum measurement actually changes the property, right? So we have to do something better. So what people have been doing so far is what is called quantum state tomography. Okay, and this is very similar to the tomography concept that we use in our, CT scan, right? T is for tomography there. So what is happening is, instead of imaging the brain with one, invasive measurement, which of course you don't want to do, they image different projections of the brain. Let's say the brain is the object of interest, and then you stitch these images together to reconstruct the image. So something similar is done for a quantum state as well, different projective measurements and reconstruction. So that is what is called quantum state tomography, okay, or QST. But then as the dimension of the system goes up, the number of measurements that is required in quantum state tomography also goes in the d square order. Okay, so you need d square order number of measurements in order to reconstruct a quantum state. So what we have done is used the age-old phenomena of interference, okay, and come up with a new technique called quantum state interferography, by which we are able to estimate the quantum state by using an interference measurement, and the number now required is of the order of d-1. So you can see that this is a fantastic scaling advantage over the conventional technique. And this, of course, is great because with the precision knowledge of the state, its application in quantum computing, quantum communication, and various other domains would become that much more precise and in control. Okay, so this is one of those very new results that we have on quantum state estimation. In the domain of quantum computing, what we are working on is some slightly unconventional. Instead of the usual qubit-based quantum computing, which you have been hearing about, we are working on what is called higher dimensional quantum computing, whereby, instead of using a qubit, what we are using is a qubit, or an n-level system where n is greater than 2. Okay, and so you already know that the advantage that we have in quantum computing comes from this exponential speed up, right? So we talk about 2 to the n, where n is the number of qubits and 2 is, of course, the number of basis states, right? So instead of 2 to the n, if you now have 3 to the something or 4 to the something, then that something drops, right? So 2 cubed is 8, 3 square is 9. So basically, by increasing the base, we can reduce the number of systems. And that actually has several advantages in terms of, what one can do with this. Okay, and so there are stated theoretical advantages in computing and communications, and we have our own system in the lab where we have a very nice entangled pair of qubits, which we are employing towards various applications and trying to see these advantages in higher dimensions. Again, if this is something which interests you, do have a look at this article which is at a popular level domain, giving a holistic view of this research that we're doing in higher dimensional systems. Okay. We are also working on different forms of quantum measurements. As you know, that is one of the very important areas of quantum science. And we are, have several applications in what are called weak measurements, whereby, in between the preparation and the measurement, by weakly interacting with the system, and this weak interaction actually, of course, has a mathematical definition and form, which I won't get into, but then by doing a statistical ensemble of measurements, you can actually figure out, okay, what is happening to the system in between preparation and measurement. And this is great because this can be done in a way that you do not change the system in the process, which is what would happen in a strong conventional measurement. So we have done lots of interesting applications of this tool. We are studying entanglement from different perspectives, the sudden death of entanglement, how to prevent it from happening, how to hold on to entanglement for longer in the lab, and many such. Okay. Now I go on to the main focus of today's lecture, which is on quantum communication. And of course, the main quantum aspect in this is in fact what is called the quantum key distribution, or the key distribution problem. And in fact, I would say that this is the most quote unquote practical quantum technology. Whereas you hear about quantum computing and other things, there are different levels of technology readiness, whereas quantum communication is at a slightly higher level of TRL, because there are also companies which are making products on QKD internationally, and it is being used by various sectors, whether it's banking, defense, and so on. So it's already in use in the public domain, as opposed to being only of research interest. But that doesn't mean that research has to stop, because there's a lot to do in terms of new protocols, in terms of higher security, longer key, longer distance, many important research problems to solve, along with the technology being already used in the public domain. Okay. Now, of course, if it is already used, then it makes sense for us to know a little bit more about it. So, but then why one should worry at all about this? Well, these are all applications which I'm sure most of us are invested in, right? Whether we are purchasing something using a credit card, doing online banking, voting for our, parliament or, legislative assembly, and then, of course, defense. Now, defense is something we are not directly perhaps involved in, but there is the defense, the whole sector, which is involved in such strategic communication. So, as you can see, all these examples that I have taken here are examples of transactions or communications which have a strategic element, right? Like if I'm going to give my banking details to a vendor online, I do not want a third party to come and know the same, right? So it is important that only the intended recipient gets this information. And so this is what is strategic communication. And at the moment, it is done through what is called classical cryptography. So essentially, you have some information, you have a key which has been distributed. This information is encrypted by one end, and then this encrypted information reaches the receiver, who again has the key to decrypt it, right? And so this way, one can communicate between the sender and the receiver. So far, so good. But then, as you can see, the important or the key element in this communication technique is the key distribution itself, right? The KEY key distribution. So it is being done by using classical techniques now. And what we know is that this will be compromised with quantum computers, okay? So we need to take steps now so that we can prevent this catastrophe, because once that happens, then all our strategic information, which is being kept secure in this way, is going to become vulnerable. Yeah. And so the solution is also in the quantum domain, and that is called quantum cryptography. So what is wrong with classical cryptography? It's not particularly what is wrong, but more like, what is suboptimal in classical cryptography. What is suboptimal is that unconditional security is not possible. So for instance, a common technique for key distribution is what is called the RSA protocol. Okay, and the RSA protocol is based on the mathematical complexity of factoring large numbers. So what does that mean? So if I give you two numbers and I ask you what is the multiplication of them, 3 times 7, let's say, 21 comes very naturally to us. But then if I now give you a number like 113471 and ask you what are the two prime factors of this number, that is not so easy to just work out and declare. Factorization is a different hardness class of problems than multiplication. So, and that is what RSA protocol is based on, this way of ensuring the key distribution is secure. Okay. And now this is Peter Shor here, who came up with what is called the Shor's algorithm. And this is an algorithm using quantum gates that can perform factorization in polynomial time. So what that means is that the hardness class of the factorization problem can be changed by using Shor's algorithm to a simpler class, which then would mean that that cannot be used to keep things secure anymore. Okay, and this will happen with quantum computing. So computational resources grow very fast, and today's hard problem could be solved tomorrow using brute force attack. New algorithms can come for classical computers also. It's not just quantum, but of course there's the realization of quantum computers which will run the algorithms like Shor's, which are already known to be of the type which will break the hardness of certain class of problems. So my security should be independent of future advancements in computational power, new algorithms, or new technology. That is, it should be future secure. And this is a very important term here, future secure. So something which is secure today, even 30 years down the line, I would like to ensure that that is still secure. So if I use something like the hardness of a mathematical problem for the security aspect, and if that hardness changes in 30 years' time, then the security doesn't remain anymore. So it, for instance, think about it, that if it is an inheritance problem, okay, and so you've left some money for your progeny, and then 30, 40 years down the line, that person is supposed to inherit this, but then by then the security is compromised, so everything is gone. You do not want that. So security should be future secure. And so this brings forth the need for quantum cryptography, where security is based on laws of nature or laws of physics and not on the mathematical complexity of a problem. So most important part is the key distribution, which is what is called quantum key distribution. Now, having said that, this, as I mentioned, the RSA being the example we are taking. So this is what it is, that, 2048-bit key, the security claim is till 2030, and a longer key even beyond 2030. But this is a very famous quote by Krista from Microsoft Research. She says that the RSA 2048 challenge problem would take 1 billion years with a classical computer. A quantum computer could do it in 100 seconds. Okay. So this kind of makes it very obvious that one has to work on a solution now. But do remember that a quantum computer will employ Shor's algorithm and to solve the factorization problem, and it is estimated that this 2048-bit RSA keys could be broken on a quantum computer comprising around 4,000 qubits and 100 million gates. And so we are not quite there yet, okay, in terms of our capability as a community. We have smaller number of qubits and gates right now in the current quantum registers that are being, developed. But that doesn't mean we become complacent, because, in a few years, quantum computing research is progressing very, very fast. Okay. And so it could be in 2 or 3 years time even that we have a quantum computer which will be able to employ Shor's algorithm to the level that it would become a problem for the current key distribution. Okay, so it's not, when I first started working on these areas, long time ago, the thing was, this is not a problem today, maybe in, several decades. So why worry? This sort of thing was there. But of course, now there has been a lot of change in our thought process. So from that sort of thing, now we have reached a level where we are having missions dedicated to working on these problems. So you can see that even globally, we have, progressed tremendously over the last few years. And so this is not a problem for our next generation to solve. We have to do that so that it is not a problem anymore. Because quantum computer will do many interesting things, and you've been exposed to many such interesting applications I saw from the program over the last few days. So let it do that, but let it not become a threat to our security. And so that is why we need the solution. And that is where quantum mechanics comes in to protect our information through quantum key distribution. Now, of course, in a 45-50-minute lecture, I wouldn't have the time to give you details about how quantum mechanics protects information, because those are, technically quite long and will take a lot of time. But then I can summarize the idea as follows, that, measurement disturbs the signal on an average, this we know, and this comes in handy to protect information. If the signals are non-orthogonal, then adversary cannot ascertain which one it is. Okay, and this is what we use in the BB84 protocol. I will show you. And that is basically using the Heisenberg's uncertainty principle. Then unknown quantum states cannot be cloned by an adversary, I'm sure you know, and this is called the no cloning theorem. And this is very good for us because an eavesdropper cannot just copy and then, send the state to the receiver, because unknown quantum states cannot be cloned. And then, of course, quantum correlations are used to protect information, like quantum entanglement. And we will see a little bit of detail of this in the next few slides. Okay. So now there are different approaches to QKD. The common classification would be into two types. One is prepared and measure-based QKD, where the security is based on uncertainty principle. Okay, and the popular ones are the BB84 protocol, the B92 protocol, and several variants of the same. Then entanglement-based QKD, where the security is based on entanglement. Popular ones among them are the BBM92 protocol, the AICTE91 protocol, and several variants. Okay. So I will, explain a little bit as to how the BB84 protocol works. Okay. So in the BB84 protocol, conventionally we have a sender who's named Alice for historic reasons, and a receiver Bob, again Bob for historic reasons. So we have Alice and Bob who are trying to, establish a secret key between them. Okay. And so Alice has access to a single photon source, very important, because, if this is not going to be a good thing, then this will have tremendous security implications. Okay. So, and this, what she does is that she actually randomly encodes this photon in one of 4 possible basis choices. So you can see that we have the horizontal vertical basis here, which is the rectilinear basis. And then we have the plus minus 45 basis, which is the diagonal basis. So she selects either, as you know, the H, we can represent it by the 0 degree, and B is 90. So she encodes it in 0, 45, 90, or 135 randomly. Okay. And so I would use this color encoding. So the rectilinear 0 is red, diagonal 0 is yellow, rectilinear 1 is blue, and diagonal 1 is green. Okay. And so she does a random selection of bases. And this randomness is very important, because if there is any lack of randomness here, then some information is then remaining, which can be used by Eve to know more than what she should be allowed to know. Okay. So this is very crucial. So she randomly selects one of them and encodes, and here, for instance, the red one comes out. Then again, it goes to Bob, who again randomly selects one of these 4 bases to measure in, and does a measurement. And so as you can see, many possibilities emerge. So she could be measuring in the R0, Bob could be measuring in D1, D0, R1. Sometimes they would match. Because it is random, you do not know, right? So this happens. And so for this selection, let's say what they do next. What they do next is, through a classical channel, they actually share the basis information. Okay. And this is very important, that it is the basis information and not the bit information. Because of course, if they actually tell over the classical channel that these are my bits values and these are my bit values, then that's gone. So there is no security involved anymore, right? So that has to be kept very much under confidence. All they can share through the classical channel is that basis choice. That is, Alice says RDRR DD, Bob says DRR DDR. Okay, that way. And they have also measured their timestamps. And so then they compare their basis choices and they realize that only for some of them they are matching, right? Because it's random. For sometimes they will match, sometimes they won't match. So they will only retain those bit values for which the basis choice is matching, because then they know that they would also have the same bits. But that is something they won't declare. They'll only declare the basis choice. So Alice's operations prepare single photons through various processes. It's possible, as I mentioned, and do have a look at the article. Random selection of polarization basis for each photon between rectilinear and diagonal basis, random selection of polarization between two orthogonal states in each basis, record timestamping and polarization state for each photon, send stream of photons to Bob. Okay, and at Bob's end, random selection of polarization basis for again each photon between rectilinear and diagonal, measure each photon in the selected basis, record timestamping and polarization state for detected photons. Together, what they do, they send the timestamping and basis selection for each photon over classical channel and compare selected basis for correlated events and consider only those events where basis choice match and discard the rest. Okay, so this is a cartoon representation of the BB84 protocol. There is a lot of detail which I did not get into, but then you get a general idea of how things are proceeding. So of course, the quantum source is a very important element, because if there is any multi-photonness in it or any randomness lacking in the encoding, it is going to have tremendous security ramifications. Then of course they would do some simulations to figure out what is their expected bit rate and error rate and so on. They would establish the protocol, which is of course important, very important, because there are many choices and it depends on what one wants to achieve in the end. And then after that, there is sifting, which is essentially this, basis selection, and then only keeping the ones where the basis choice matches. Then they do some classical post-processing steps, which are privacy amplification, error correction, and then they end up with a secure key. Okay. Why do we need entanglement in all this? Because we've just seen that this is being done in a single photon level without using entanglement. However, having said all this, as you may have realized that, in order to do all this, there are several devices which are being used by Alice and Bob in order to achieve the end goal, whether it is the photon source itself, whether it is the encoding operations, whether it is the measurement, many devices are used in this process. So how much do we trust our devices? Okay. What about security vulnerability, which may be introduced at the device level itself? So what we want to go towards next is QKD, which is device independent. So essentially, we do not worry if the devices have any vulnerability, and still the protocol is secure. And so entanglement-based QKD is the only known route towards device-independent QKD, and longer distances are also possible through entanglement swapping-based repeaters. And so that is why entanglement-based QKD has a special role in the QKD domain. Okay. Going on to our research at RRI Bangalore, again in a nutshell, various things which we have been doing. Well, of course, we have doubled and demonstrated various types of protocols over the last several years, prepare and measure-based protocols, where we use uncertainty principle for the security. This is our, demo experiment for BB84 around 4 years back, where we had, done the demonstration of BB84. A couple of years ago, we did what is called the B92, but then again, a new take on the B92, where, again, without going into the details, this is also a single photon based protocol. But here, instead of four possible choices for the encoding, Alice has 2 possible choices. And on the other hand, Bob also has 2 possible choices for his measurement. Okay. So basically, we reduce the number of encodings and decodings. And that is why it is, somewhat more attractive, because it kind of reduces the resource requirement also. Okay, but then so essentially random selection, as I said, between 2 choices, and skip the details, but the idea is that they compare their timestamping data and consider only the correlated events and discard the rest. So there's a lot of commonality with the BB84, but then a fundamental difference that here we are dealing with only 2 choices on one end and the opposite 2 choices on the other end. Okay, and then this is a an example of how the measurement outcomes can look. And as you can see that, when they have this, so here, as I mentioned, that, this is H minus, so Alice was V plus, right? So here we retain these, right? So H, D, and then of course the plus V and so on. And so the rest is discarded, okay? And this is our, schematic for our B92 protocol. And we did the protocol using spontaneous parametric down conversion based sources, okay? And not weak coherent pulse, which is the more standard way of doing B92. And I will tell you a little bit about why. So this is a snapshot of our experiments. And of course, given the time constraint, there's only so much one can say. Do have a look at our paper here, where there's a lot of detail on the experiment and attended calculations and so on. And so this is a schematic. Having said that, this is a very important thing that, what kind of key rates and Q bar did we achieve? So we have a channel length of around 2 meters. And for this sort of crystal parameters, we have a key rate of around 50 kilobits per second and a quantum bit error rate, which is restricted to 4.8%. So 4.8% is what is called the information theoretic security threshold for B92. And this is very important. So, just if you say, okay, we have done this and this is our protocol and here is the key rate and Q bar. But then not everything is useful later on for the security purpose. The error has to be below a certain threshold, which involves very hardcore information theory based calculations, which guarantees that if it is below that, only then it can be further processed with privacy amplification and error correction to be used for security. If it is beyond that, then it's too much error, okay? Either it is from experiment or from eavesdropping, but then that is not allowed. So this is the threshold for B92, okay? And to our knowledge till date, the best available B92 setup using SPDC source had reported a key rate of 31.6 kilobits per second and a Q bar of 10.5%, okay, for 0.4 meters transmission. So clearly, our SPDC-based experiment has a much better, much higher key rate and a Q bar restricted to the information theory bound. And so definitely much better numbers from the known literature using SPDC. We introduced several novelties in our setup in order to actually achieve this. Okay, so as I mentioned, using SPDC process, we did this, and so this has a significant advantage in terms of security, because we have much less multi-photon generation in SPDC than the more conventional WCP used in B92. Then we have used true randomness. As I mentioned earlier, the randomness is very important. So we have used photon on a beam splitter, so which path information based randomness, as opposed to using a pseudo random number generator, which is what people tend to use. Okay, we have actually correlated polarization with the temporal degree of freedom, and this modification makes the protocol tolerant to external noise. And then we have achieved a very high key rate and a low Q bar. And as mentioned, this is the highest value achieved in a heralded single photon based B92 setup to the best of our knowledge. Okay, and also the Q bar is lowest. Yeah, and of course the students used these keys to actually encode and decode an image, and so this is what the encrypted image looks like. And of course you can see that it's very successful. If it wouldn't be successful, maybe we would end up with that. Okay, and so this was our first B protocol, which was a take. Not first protocol, but a novel one, which was a take on the B92, but then with all these modifications. And in fact, the paper that I mentioned, do have a look, that is indeed, India's first reported free space quantum key distribution experiment, which is published in an international forum. Yeah, so I'm sure you will like reading that. We have also done entanglement-based QKD, and so this is a schematic of one of our entangled photon sources. Okay, and this is the snapshot of the source, Alice and Bob setups. Okay, and we achieved a very good concurrence. Concurrence is the measure of entanglement. So how much entangled is your source? So we achieved a 0.99, highest value being 1, and of course that means that this has direct ramification on how secure the protocol that we performed went on to be. And so this is, the reference, do have a look. And we also have a patent application. So going on to that, one of the things I wanted to talk to you about a little bit, the other aspect in that paper, now of course that was the first experiment and so on from India, but then the other important aspect of that paper was that we actually established a very interesting simulation toolkit for QKD, okay? And so, in fact, that achieved a lot of, public attention, and people were very happy with this development that we had. Okay, and there are lots of simulation toolkits which exist for QKD in literature. If you search, you will find these and more. But then none of them actually satisfies all these requirements together. So quick and precise simulation of physical processes, considering realistic experimental imperfections, simulation of the single photon source, detection module, and background noise in more detail, and generalization and applicability to all existing protocols. So what is interesting is that, with QKD becoming commercially viable, advanced engineering techniques are being proposed, right? Now, direct testing of these techniques in an optical setup is not very cost effective. So just imagine, you come up with a protocol and then you ask for funding and you say that, I want to do this in the lab and see whether it works or not. But that is something which is very difficult to invest in, right? Because it's finite amount of investment. You don't want to invest it in actually buying the components and setting it up and then realizing that maybe it is not good enough. So this is where QKD SIM comes in. QKD SIM helps in quick accommodation and testing of these techniques by enabling simulation of QKD protocols, considering physical process models, realistic imperfection, and experimental non-idealities. Okay, and so this is very important because simulation kits so far, the software that is available is perhaps developed by software developers, right? So they are not experimentalists, so they don't really understand that experiments suffer from imperfections, right? As they should. Components will have some imperfections, the processes will have imperfections. So all that should be factored in. Only then, you'll be able to have a realistic prediction, okay? And so we have tested QKD SIM's performance with our implementation of the B92. Okay, and so what we do in QKD SIM is follow what is called this agifall model of software development. So it's a waterfall structure, top down, but with agility at every layer. So if tomorrow we come up with a better simulation of one of the modules, we can replace that module. So it's a modular development, and so easy to replace with better modules as and when they are developed. Okay, and so this is what is called the hybrid of waterfall and agile model of software development. And we also did a lot of research and analysis in different optimization techniques so that we can actually have this, restriction of the QBA to 4.8%, and then, also play around with key symmetry. So the number of zeros and ones, that is what is called the symmetry. So if you have a 100-bit key, then 50 zeros and 50 ones is a perfectly symmetric key, right? But then you can always have 51, 49, and so on. So if you have too much asymmetry, then, and that is something then, is known by Eve, then that can be a security loophole. So we have investigated different options of what kind of security ramifications different types of optimization techniques would have. And so details are here. And the comparison of the simulation result with experiment is very nice. As you can see that both the simulation and experiment predict around a 50 kilobit per second key rate, and the QBA is restricted to 4.8%. And as I mentioned, we also have now a patent application on this, and new developments are happening, which are making these things even more stringent and precise. Okay. And this is a snapshot of various algorithms that we had developed. Now, going on to the focus of our lab, which basically happens to be in the domain of long distance quantum communications. Now, why do we have distance limits for quantum channels? So, okay, you see, so in ground based QKD, where, the sender and the receiver have line of sight. So beyond a point, you cannot have line of sight, because of course, even the Earth's horizon will come into the picture, right? So typically 100 kilometers is okay, it's possible. Maximum with a lot of stretching, maybe up to 300. But you cannot go beyond that with free space because you don't have line of sight. Then comes optical fiber. You can replace the optical fiber, which is how classical communication currently is done, right? Or our internet, so on and so forth. It's through fibers. But then the problem with using this directly in this domain of long distances, that beyond a certain distance fibers have loss, right, as you know. And so beyond a certain distance you will have to boost up the signal, which will involve some sort of an amplification, and optical amplifiers won't be possible in the conventional sense because of no cloning theorem. You cannot just boost it up without violating no cloning. So you have to think of out of the box solutions for long distance. And so there are, few being investigated worldwide. One of them is called the trusted repeater based technology, where you have these trusted node based fiber based networks, where after every distance, let's say 100 to 100 kilometers, there is a node. and then that node becomes the new Alice, and then Alice to Bob, Bob 1 becomes Alice, and then Bob 2 becomes Bob, and so on. So that way you can go on for some time, but then you have to trust these nodes. If one of these nodes becomes compromised, then the security is gone. Then there is the quantum relays and quantum repeater technology, which is what we are investigating under our project under this DST's umbrella program called Quantum Enabled Science and Technology Program. And then there is satellite-based quantum communication. Okay. So as I mentioned, we are investigating the quantum relay repeater approach under this problem. So this is actually, in a simplistic sense, similar to the relay race that we all used to play when we were much younger, right? So you have these two parties and groups of people, and so one person carries the baton, goes over to the other end, hands the baton over to the person on the other team, and this guy then comes and gives it over to the girl here, and so on and so forth. So there's an exchange of the baton, and ultimately it lands up on one side, right? And so this is what is called a relay race, if you remember. And so this is what we are now doing in the quantum domain by exchanging entanglement. Okay, so this is called entanglement swapping. So here I have an entangled source, 1 and 2 are two photons which are entangled. Here I have another one, 3 and 4 are entangled. By doing what is called a Bell state measurement between 2 and 3, I can transfer the entanglement to 1 and 4. Earlier 1 and 4 were not entangled, but now they are. This is called entanglement swapping. So entanglement swapping can lead to quantum relays, which is a way of increasing the distance. But beyond a point, you will need a quantum memory also thrown in, and that is called a quantum repeater. Okay, and so this is some project that we are investigating. Going on to satellites for QKD. Now, satellite is something which bridges the large gap between ground-based networks. So essentially, you have a satellite; it spends some time on a ground station, and then exchanges a key. Then in its path, it crosses another ground station, exchanges a key, and then by performing certain mathematical operations and details, these two, one of them can be used to secure the other one, as a result of which these two ground stations, which were originally not linked by anything, are now linked by a quantum link. So they have exchanged a key between them by using the satellite as a trusted node or a trusted courier. Okay, so it's going from one to the other and aiding in long distance QKD. Okay. And so different distance levels are possible using these different approaches, and this is a snapshot of that. So the idea would be to go towards combining all of them, which is what we call the global quantum communication network. Okay, so here we have satellite QKD, which is connecting two nodes which are at a very long distance. Now this node then sends the key to different service providers, maybe through a fiber-based network. So fiber, satellite together can connect up different parts of the country, and then at the next step, different countries, which is what is called the global quantum communication network, which is what we would all hope to see, at least in some of our lifetimes. Yeah. And different approaches being taken by different countries towards long distance quantum communications. The only, satellite which exists currently, which has demonstrated some of these ideas, is from our neighboring country. And this happened 2-3 years ago. And other than that, there is no, as of now, no other quantum satellite which has actually been launched. Okay, and so there are different countries which are approaching different parts of the problem. And here we have our project, which is Quantum Experiments with Satellite Technology, or QUEST, which is a collaboration between RRI and ISRO, and which started in 2017. Okay, and so this is essentially the idea. So we have a satellite which is exchanging a key with the ground station here. This is the one which is closer to me, let's say, and then it moves, exchanges a key with the second ground station, and as a result, establish information theoretically secure communication over large distances. Okay, QKD between two ground stations. And so this is India's first project on satellite-based QKD. And of course, we want to establish satellite-based quantum communication between two ground stations in the country using an Indian satellite. But then as an offshoot, we also want to establish a key with Canada. Okay, and essentially, take a step towards different countries being linked in quantum communication towards the global quantum communication network. So that would be several thousands of kilometers, and hopefully it will succeed. And that would be very nice as a distance record. Okay. And these are our portable ground stations at RRI. Okay, so this is our one of them with the telescope inside and so on. And so this is what we have very recently achieved as in 2021, January. we were able to demonstrate free space quantum communication between two, labs at RRI. So this is the Alice lab, this is the Bob lab, and inside here we have the entangled photon source, which is Charlie. So over a distance of 50 meters, we were able to show quantum key distribution using entanglement as a resource, using an atmospheric free space channel. Okay, and this is again the first such demonstration from India on free space quantum communication using an atmospheric channel. And in our in-lab entanglement-based protocol, we had very nice key rates, as well as, the Q bar restricted to the information theoretic bound of 11% this time, because the protocol has changed. It's BBM 92, and this was in 2020. And then, as I mentioned, in January, February 21, we demonstrated this atmospheric channel-based QKD with, encouraging key rates and Q bar at the time. And over the last, of course, we had a couple of months of lockdown after that, but then now we have picked up again, and we are, optimizing the key rates and Q bar as we speak. Okay. And again, we are very happy that this particular demonstration also garnered a lot of, positive reactions from various sectors. Yeah. Okay, and this is some of the people who are inside the dome aligning the telescope. And of course, this is the condition since 2020. This is how we are trying to work. And of course, hopefully our enthusiasm still remains very strong, because we are able to achieve different firsts as we go along. Okay, and very nicely and very encouragingly, the DST also recognized our work as one of the 20 major success stories of 2020. This work, as well as our quantum state estimation problem. So this was recognized. And also India Science, which is our country's science channel, as you know, which is a collaboration between Vigyan Prasar and the DST. They also recognized our work as one of the top 10 inventions of 2020. Okay. So as I mentioned in quantum communications overview, we are working on India's first project on satellite-based QKD, but we're also working on different other aspects of quantum communication. This is integrated photonics-based QKD. It's more like something QKD on a chip, which if it succeeds will actually make it possible for you and me to use it even in our, daily life. So QKD for the common man. Then we are working on quantum teleportation relay and repeaters under the DST program. And then under the MITE Center for Excellence in Quantum Technology, which our lab is leading from RRI, we are working on different aspects of random number generation and fiber-based teleportation and so on and so forth. As I mentioned, and as was mentioned earlier, I'm an invited member of the focus group on quantum information technology for networks, which has been formed by the ITU, United Nations. And the aim of this group is to actually come up with standards for quantum technology. So while, we are demonstrating different protocols, there are other labs which will demonstrate different things, at some point, we have to compare it with some expectation from a global standard. It's almost like the ISI mark for quantum. And so this is what we are working on towards establishing, so that there is some basis which various results can be compared against. And it is through this interaction that I am privy to different, things that are being done in different countries towards this field. And so, for instance, this is this satellite-based quantum key distribution demonstration, which was done by, and you can see details here. And then there are some efforts which are happening in Russia as well. Towards different test beds. Okay, industries are coming up which are working on different aspects of QKD. This is their satellite QKD roadmap, the Russian. There is the National Quantum Communication Backbone Channel, which was established between Beijing and Shanghai, which is a 2,000-kilometer network. As I mentioned, this is this trusted node-based idea. This is the market for QKD system, which was actually, a survey which was dedicatedly done by this company. Okay, to see what kind of market share QKD would have in the next few years. So here we are in 2021, but if you go, you can see that it is almost an exponential growth that is predicted. And if we zoom in, we can see different sectors are going to contribute. Of course, military is there is civil government, but there is also other public and private sectors which are expected to have a major market share in QKD. So it's a very interesting area from different perspectives. Okay, so I think I'm on time here, and so I wouldn't take any more time. So this is, some pictures from better times. This was the last physical conference that, in fact, we had organized in January 2020, just before lockdown, last year's lockdown. And so we had lots of international dignitaries visit and so on. It was very nice. And we really look forward to such times, hopefully, in the near future. This is a snapshot of various visits. And I like to show it now with a positive outlook for what may happen in future. So with that, I would like to stop. Thank you very much. Dr. Das.
Jadav sir.
Hello, madam.
Yes,
one question
I am
is there.
audible?
No,
Hello?
your voice is cracking. I am saying.
Yes.
Okay, not clear.
Will I say, Jadav?
Voice is clear.
Not clear.
My voice is clear.
Okay, you can
Okay,
carry.
Mr. Because then you can ask the question. Yes, you can carry.
Madam, one question is there from the panelist, from Professor Utpal Roy. Kindly, if the classical channel in BB84 protocol is not secured, does it hamper the overall security of QKD?
Yeah, that's of course. This is a very good question. So, I mean, see, the classical channel is a separate thing, right? So, the classical channel is not really, contributing to the security of QKD. So, the answer to this question is that no. What we do is that we have a pre-authenticated channel in the classical domain. So there are certain steps which we, of course, there are many steps which we didn't discuss here, but then, there is an authentication that is done earlier to ensure that it is indeed Alice and Bob who are talking to each other. And so that authentication also holds true for the classical channel, but the classical channel is only used for sharing the basis information, as you can see. So if there is some lack of security there, then there might be some errors which in that sharing, but then nobody can knowingly do anything to hamper the key distribution, because the key distribution only happens for the matching basis choices, right? So essentially, maybe there will be a little more error coming into the overall thing if there is too much noise going on in the classical channel, but then beyond that, what we are left with is secure because of uncertainty principle. So that will remain. Okay. And so then later on, of course, we will use this key for the message transfer and so on. So that part we never discussed. So it's a key distribution which needs to be secure. After that, the key can be used and it will be secure because of the underlying quantum phenomena. But then, I think I'll stop there.
I think Professor Utpal Roy has got the answer. And now another question is from Partho Sarathi sir. How the basis is generated physically?
So of course, we talked about the plus minus and the RL basis, right? So then essentially these correspond to different polarization states of the photon, which is one example. So I have taken the polarization example because it's easier to motivate. So essentially what we need is, the horizontal and vertical polarization states, which will give you the RL basis, and then you have the plus and minus. And so if you have a certain polarization that the photon already has, then one can use, birefringent material to actually change this. So for instance, there's something called a half-wave plate, which one can use to rotate the polarization state from one to the other. And so the half-wave plate angles will then determine what is the ultimate encoding. And then this angle choice is done in a random manner, so that, the security is maintained. So it's essentially a polarization if you take the example, then half-wave plate would be the operation which would give you these 4 possible choices.
Madam, he has said, Partho Sarathi in continuation has said, is it an every hop the basis is generated, or it generated only at the both ends?
Not sure about the concept of what would mean by the hop here. So for every key that is established, there is a random selection of basis on Alice's end and random selection of basis on Bob's end, right? So let's say one bit is going, then there is a random selection which has generated in this bit being produced, then that reaches your receiver, and the receiver also does a basis choice to measure. So every time the bit is transferred, maybe I will interpret that as the hop. There is a basis choice that is going on both ends in a random manner.
Oh.
Yeah.
Okay, madam. Both of them has said that, Utpal sir has said that, thank you for your very much nice deliberation, or got the answer.
Sure,
Okay.
thanks.
And also Partha Sarathy sir has said, thank you, madam.
Most
And
welcome.
another question, I will take one question from here. So Ashok Nath sir has said, what is the scope from hacker's point of view to hack the data from quantum key distribution channel?
Yeah, so I mean, that is the point. So we would call the hacker as eavesdropper, right? So eavesdropper, actually, in our domain, we are always assuming an eavesdropper who's omnipotent. So essentially, the eavesdropper has, if there is something one can do, the eavesdropper can do it. So eavesdropper has all the power, is how we proceed. And that is what forms the basis for this information theoretic calculation that is done to see what kind of mutual information is shared between Alice and Eve, Bob and Eve, and Alice and Bob. Okay, and so based on these calculations, we are able to determine the information theoretic threshold. So now, if the eavesdropper comes in and does any eavesdropping, of course, he or she is going to leave some kind of signature of this eavesdropping in the quantum channel. If it is the prepare and measure, then you can easily see that there's going to be only a certain percentage in which the eavesdropper is going to be able to guess the right choice, and for certain others he or she won't. And so if this happens, then of course that will leave a signature. In the entanglement based protocol, the entanglement measure will change. So we allow up to that threshold value for this to happen, whether it is classical errors which are coming in or the hacking. Together they can contribute up to that threshold value of error, but beyond that it is not even acceptable. So we discard any such run of the experiment where the error is beyond this threshold. So up to that it is okay, and then we can get rid of it through the classical post processing, which is privacy amplification and error correction. Yeah.
Thank you, ma'am. Thank you for explaining those things. So we have already our next speaker in the queue. So
thank you very much.
Participants, if you have any queries left, you can mail us
Madam,
directly
just wait for a
to
moment.
Research Sina.
No, I'm around. Yes.
Yes, that's good. So you can directly communicate to Professor Sina, and Prem can kindly display.
Prem, please display the certificate.
Display the token of appreciation, please. Prem, are you there?
Prem?
I think not.
Yes,
Okay.
displaying.
Okay.
Displaying.
Okay.
Madam, this one is a.
Thank you, ma'am. That is a little token of appreciation from our end, and thank you very much again for giving your some precious time to us and deliver such a nice lecture. We have got too many information about quantum communications, and hope we will have your time in future also. Thank you, ma'am. Thank you very much.
Absolutely, it was my pleasure. Thank you very much, and thank you for the token of appreciation as well. Thank you. Yeah.
Thank you.
Thank you, ma'am. Thank you. Thank you. Have a nice day, ma'am.
You too.
So
Bye.
we have our okay. So we have our next speaker with us, Dr. Siddhartha Bhattacharya. So before starting the session, I would like to introduce him with the participants. So Dr. Siddhartha Bhattacharya did his bachelor's in physics, bachelor's in optics and optoelectronics, and master's in optics and optoelectronics